In this video, we'll cover the problem number of islands. We'll be given an input, which is a grid, or a 2D array, that will exclusively consist of zeros and ones. Zeros represent water, and ones represent land. We need to count the number of islands that are present in this grid and return that value. Islands are what you would imagine they are. They're just groups of land that are connected. And the way we define a connection is going up, down, left, and right. So if we look at this one right here, we can go up, down, left, and right. We cannot go diagonally. So you cannot go up here to this one. That's not valid. But you can go up, down, left, and right. Those are considered to be connected. So as an example, you can imagine that this is one island, because all of these ones are connected going up, down, left, right. You can sort of start at one of these ones, let's say this one, and only moving through our connections, up, down, left, right, reach any of the other ones that are in this island. You can go this way, and then, you could go down here or here or here. They're all interconnected. So that's considered a single island. Actually, let's grab that back. But this would be considered a separate island because you cannot travel from this one to our island over here on the left. You would have to go diagonally, which is not valid. So in this case, we can keep those again. You can see that there are a total of 3 islands present in the input grid, at least for this example that we're looking at. I've circled them here, and that's why our output is going to be 3. In terms of how this is a graph, we've kind of touched on this before, but you can think of each of these zeros or ones as a node, and the edges between them are just going up, down, left, and right. So you can go from 1 to 0 like this, or you can go from 0 to 1 like this. So those are undirected edges like this. And you can imagine this one node up here doesn't have anything this way or this way, but a lot of them do. Like this one here, let's say, has undirected edges in all 4 directions. So you can see that even though this isn't presented as a graph and we're not getting this like array of edges like we normally do, you can still see how there are nodes or vertices and edges connecting them, which allows us to model this as a graph. Now, really, this question comes down to counting the number of ones that are present in the grid, which is not that hard to do. You just iterate over the entire grid and just increment a counter every time there's a 1. But the key is that you don't want to count one island multiple times. So if you counted this island and you just did it the standard way by only counting the number of ones in this grid or matrix, you would count this island 5 times, which is obviously not correct. There's only one island present here. So what we want to do is count the number of ones present in the input grid or matrix, but make sure that once an island has been counted, we don't count any of the other ones that are on that island. This is where the BFS comes into play. Actually, we can keep that. I should stop erasing it. But what's going to happen is we're going to traverse this in a standard way. So we'll knock out this 0 node and then this 0 node, and nothing happens with those. They're not ones. Then we count this node. And before we move on to this 0, we want to go ahead and traverse this entire island that's present here. And sort of somehow mark that these nodes have been handled. We don't need to worry about them anymore. You might know that we could use a visited array or set or something like that to track this kind of information. And that is 100% valid. We certainly can use a visited array or a visited set or whatever you want to note that, hey, all 5 of these ones have been visited. In the future, just go ahead and skip them. And that is a valid way to solve this question. But I want to show another way that we can do this, which is really the same concept, just in a different way. If we are allowed to modify the input grid or matrix, and that's an important if, before you even throw out the strategy, definitely worth asking your interviewer, is it okay for me to modify the input grid or matrix? If they say no, you should go with one of the visited solutions, a visited set, a visited array, whatever you prefer. But if they say yes, we can save some space complexity by not creating a set or array. And instead, what we'll do is just say, when we mark this node, let's flip it to a 0. So this time, I actually do want to erase it. So we'll, traverse the 0 node, and then the 0 node, and then this 1 node. And we're going to say, all right, we've incremented our count. Now turn this into a 0, like this. Oops, I don't need an oval. But we can just turn it into a 0, and then explore all of the neighbors or children of this 1, which basically means, cover this whole island that we're currently on, and turn all of them into zeros. So we turn this into a 0, and this into a 0, this into a 0. That was bad. Like that, and like this. And all of a sudden, now we continue iterating. We go here, 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 and then when we get here, we won't even try to increment our count because there is no 1 there. It's just a 0. So this is sort of a clever optimization you can make if you're allowed to modify this input grid or matrix. And that really covers the core of what our solution is going to do. We're going to iterate through the matrix. We can actually go ahead and pseudocode this out on this side. So we are going to iterate over the matrix and bump our count. So iterate over matrix. We can put this in one step. We can say iterate over matrix and count the number of 1s. So I'll just say num of 1s. But we want to do this key step, which is that after we find a 1, so I'll just say find a 1 arrow, which means something we do after we find a 1. We want to convert the whole island to zeros using a BFS. That's an important note that I didn't stress enough. But we're going to use a BFS to traverse that entire portion of the graph, which is the entire island. So I'll just write a little asterisk and say using a BFS. And that's really it. That is what we do to solve this question. The key piece is going to be how we execute the BFS carefully, because you can imagine when we are on this node, we're going to try to go up, down, left, and right. So going down, left, and right is totally fine. I have so many arrows. Let me erase the arrow showing what I'm pointing to. Okay, but this up arrow is invalid, right? We're going to have a row of -1 if we try to go to that position. And, if we try to search -1 within our grid, that's not good. It could lead to problems. So we want to handle that explicitly and make sure that we're careful about what happens when we go out of bounds. That's sort of one of the curveballs that comes along with this question. Okay, now I want to talk about the complexity of this solution because it's a bit interesting. So we'll start by defining our variables. I'm going to say R is equal to the number of rows in the input matrix, and C is going to be the number of columns in the input matrix. We've discussed this before, but some people like to use different variables like M and N. That's totally fine. I just find this to be a little bit clearer, but feel free to use whatever you want. As long as you're defining your variables, it really shouldn't matter what letters you use. Okay, so our time complexity is going to be O of R times C. Like this. And let's make that C better. The reason is this part should pretty clearly tell you that it's going to be O of R times C, at least on the lower bound, right? Because we have to iterate over every single node in the matrix, starting from the top left all the way to the bottom right. How many are there? Well, there are going to be R rows right here, and there are going to be, they're going to be C, that was ugly, but it's okay. There are going to be C columns here, so R times C entries that we have to go through. That's not too complicated to see. The question becomes, why is it not more than R times C, or R squared times C squared, or something like that? Well, let's think about the logic that happens at each one. Let's say the entire grid was full of 1s. We would hit the very first spot, and we would do a BFS that goes through the entire grid. But then after that, so that BFS touches the whole grid once. So that's like R times C, just that one BFS. And then a second time, we're going to iterate through all of the other nodes, but they're all going to be zeros now because we would have flipped them to from 1s to zeros. So we're not going to start another BFS from that node ever again. So you would notice in that scenario, we touch every node twice. We touch it once through our BFS, and then a second time as we're iterating over the entire matrix. So you would see the time complexity there would be O of 2 times R times C, which is just R times C, because we can drop that constant. So that explains the time complexity. The space complexity is a little bit more difficult, a little bit it's a bit difficult to see. So it's actually going to be the max of R and C. And let me show you why. So see, we're not tracking any visited information, right? We are, but we're using the input matrix to do that. So we don't have an extra array or something that would use space. So our space complexity is going to come from what is the max number of nodes that could be on the queue at any one point in time. And to figure that out, again, imagine if the entire array was full of ones. Then we hit this first node, and we're now going to BFS through the whole array. Let's just say that we set our code up so that we go to the right first. What would happen is we would start at this start node, and then we would go to the right and to the right, and I won't draw all the arrows, but we would be covering this whole portion, and they would all be on the queue at one point in time. So in that scenario, we would have, C. This is of size C. Right here, because it's just the number of columns. So that would be C, would be our space complexity, O of C. But the same thing could happen if we had written our code so that we go down first. It could have been like this, and we would get O of R. The reality is our code has to start going some direction. And if you think of the worst case of our input, that direction is going to sort of be abused in a way, meaning that, there's going to be some input that is skewed very weirdly in that direction so that you end up traversing the entire graph, or like an entire row or column like this, and having that entire row or column on your queue. So really the larger of these two, whichever is larger, the R or the C, is going to be the upper bound for your space complexity, because if you get a worst case input for your specific implementation, then you could have the entire row or the entire column sitting on your queue at one point in time. Okay, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've imported our queue, and I've also set up the example input and output. At the bottom, I have a simple test case to make sure that this function works, and I've set up the skeleton here. Okay, so let's go ahead and get to coding out the solution. So the first thing I want to do is just grab the number of rows with grid.length and grab the number of columns with grid at 0.length. We're kind of assuming that every row has the same number of columns here. There is one edge case, which is that if the number of rows is 0, then doing grid at 0 like this could potentially break, and we would get an error where we're trying to do grid at 0, which gives us undefined, and then we do .length, and that's not going to work. So we want to just say if the number of rows is 0, not 0.9, let's just go ahead and return 0 because there are no islands in an empty grid. All right, now we said we want to go ahead and iterate through the entire grid. So let's say our row is going to start at 0 and it's going to go, I'm in the habit of writing I. Going to go through num rows and row plus plus. Same thing for columns. Keep typing that. Columns less than num columns and column plus plus. So this just gives us every position in the matrix. Now, what do we want to do? We want to have a counter up here that's going to be num islands, just going to be the number of islands that we have. And every time we find a 1, we want to bump that counter. So let's just say, well, let's grab the value. So let's just say value is going to be grid at row at column. And then we'll say if value is equal to 0, let's just continue. We don't need to do anything. So at this point, we can assume that we have a 1. So what does that mean? It means, first of all, we found a new island. Let's bump our counter. And then we also want to convert island to zeros. So let's say we'll write a function to do this in a second. But this is just going to go through every node that is connected to the current node and set them all to zeros. Assuming that works the way we want, we can just go ahead and return the number of islands here, and we should be good to go. Now, let's think about what this function needs access to. We certainly need the grid, the row, and the columns, so we know our positioning. And I think that should be it. And if we need anything else, we'll find out in a moment. So we're going to we'll come up here. It's going to take the grid, the row, and the column. And what do we want to do? So this is how we're going to use, where we're going to use our BFS to convert the entire island to zeros. So we'll start with the standard BFS that we know. We're just going to create our queue. We're going to add our initial position. Now this is important. We want to be able to uniquely identify what position, like what square or portion of the grid we're looking at based on the information here. So we can't just say like what the value is. Like if I just told you we're at 0, you don't know which 0 it is. To be able to uniquely identify a position, we need the row and the column. So we're going to have arrays be the elements of our queue, and the 0 index will contain the row, and the 1 index will contain the column. All right, now we can go ahead and say, so long as the queue has elements in it, what do we want to do? First thing is we want to grab the row and the column. Like this is going to be whatever we get by dequeuing. And this is using array destructuring, but that's definitely not necessary. If anyone isn't comfortable with that, you can totally do it like this. You're going to grab out the node, and then you'll say row is going to be, oh, you know what? We already have row used up here. So let's go ahead and change this to current row and current column. And here we'll make this current row is going to be node at 0, and current column is going to be node at 1. Either of these syntaxes is totally fine. They're doing exactly the same thing. Here we're going to have our process node step. We'll leave that blank because that'll take some more thinking. But we also want to add the neighbors of this node onto our queue. Now remember, we can only go up, down, left, and right. So we'll just handle those cases explicitly. So we want to say push onto the queue, and let's say first we want to go up. So how do we go up? Well, we take the current row and the current column, and what do we want to do? We want to say stay in the same column but go up 1 row. So we want to go -1 on the current row. This is an important place to be careful with what you're saying. I've seen a lot of people mess this kind of stuff up, where they'll say like, you know, we're going to the right, and it's not really going to the right. So be careful here. Let's make this one be down. So that's just going to be the opposite of this. We'll make it be +1. We'll go 1 row forward. Then we will push cur row, and we're going to do cur col -1. So that should be left, because if you're in this fixed row and you move the column to the left by 1, or to the left by 1, that moves left. And the last case is going to be current row and current column +1. And this is moving to the right. So you stay where you are, but the column moves forward and you go to the right. Honestly, it doesn't end up mattering. Like as long as you cover all 4 cases, it's fine. But in an interview, you don't want to be saying the wrong thing and, you know, making yourself look not ideal. So just be careful when you're working with those. Okay, so this is the skeleton of our BFS. We don't need to return anything, so we don't have to worry about that. Now, the only thing we need to think about is what do we do at this process node step? Well, the goal of this function is to convert everything that is connected to this island to a 0. So let's just say grid at current row at current column. We're just going to set it to be a 0. That takes care of what we want to do. But there are a couple of other scenarios that we need to handle. The first is what I talked about, where it's possible for a node to be out of bounds. So we want to handle that. And we also want to handle the scenario where we hit a 0, right? Because right now we're adding every neighbor to the queue. But if we hit a 0, we don't need to continue BFSing past it. We can just stop. So those are the 2 things we need to handle. So we can actually do it like this. Let's say if it's not a valid position, let's say is valid position. This is a function I'll write in a second. And we'll pass grid, current row, and current column. So if it's not valid, or what? Or we can, we'll say or grid at current row, current column is equal to 0, then let's continue. So let me explain what the thinking is here. So this function is just going to tell us if we're in bounds, right? It'll return true if it's a valid position. It'll return false if it's bad. So we're saying that if this is an invalid position, just go ahead and continue. I don't want you to try to set it to 0 because that'll give us an error. I don't want you to try to push anything. Just stop because we're out of bounds. Or if the value is a 0, which means it's not land, it's just water, we don't have to continue, it's not part of this island, then just go ahead and move on if either of these are true. The reason I paused is I was thinking that we could do something like this, like current value here is going to be grid at current row at current column. And that way right here, we wouldn't have to write this out. We could just say current value. The problem with that is we don't know that as of line 29, we have valid numbers. We could have something that's out of bounds like -1. We don't check for that until right here. So this current value line on line 29 could cause a problem. So we should not do it that way. We should just check it like this. All right, now we want to quickly write this isValidPosition function. And you definitely don't need to write this as a separate function. I just chose to because I felt like it, but it's fine to do it in one function as well. So you can say, you could write this in one line. I'm going to write it in a slightly more verbose way, just because I think it's a little bit more readable. So we'll say if the row is less than 0, or the row is greater than or equal to grid.length, which is the number of rows, then let's return false. It's not a valid position. Similarly, if the column is less than 0, or the column is greater than or equal to grid at 0.length, and remember grid at 0 is valid because we checked for that right here. There's at least one element in the grid array. So if either the row is less than 0 or greater than or equal to the number of rows, or the same thing for the columns, we should return false if any of those are the case. Otherwise, we should return true. Again, you can do this in one line. I just think this is a little bit easier for me personally to reason about. Okay, so the key with this BFS here is really the step where we're processing the nodes. Number 1, you have to make sure everything is valid. And number 2, make sure you're actually dealing with a 1. Once that's the case, just go ahead and set the current position to 0 so that we will never worry about it again. And then add all of the neighbors onto the queue. And if they aren't 1s, then we'll handle that right here before we ever try to convert them, which wouldn't do much anyway. Okay, so since we already have our test set up here, I think we can go ahead and verify that everything is working. We should get an output. Oops, this is wrong. We should get an output of 3. And let's see if we do. So we come over here, we can clean this up, we run this, and we get an error. Let's see, queue.push. Oh yeah, sorry, queue is the queue class. So we're not supposed to be using push there. We want to use this enqueue method. My bad. So we save that and let's Control L and try again. Okay, great. We get 3, which is the output that we were hoping to get. All right, now let's talk about the complexity of this solution. So we can define our variables initially. So we'll say R is going to be the number of rows, C is going to be the number of columns. So we said our time complexity is going to be O of R times C. That's pretty easy to see from this loop. And we also mentioned that our BFS is only going to go through every node in the graph once, in the very worst case scenario, assuming they're all ones. So we would have 2 times R times C, which just gives us R times C. In terms of the space complexity, this is going to be the max of R and C, because we talked about the maximum number of nodes that will be on the queue or in the queue at any point in time. It's going to depend on R and C. And you can see in this example, we're going up first and then down, and then left and right come later. So you can imagine we would, like if the entire matrix was a bunch of 1s, we would start here and then we would go down, because up doesn't mean anything. We would go down and then down and then down, and we would just keep going this way. So however many rows there are, we would fit all of those onto the queue at that point in time. If you reordered these and you went to the right first, maybe you start here at this one, assuming they're all 1s, and you go all the way here through the number of columns. That's why it's the max of R times C, because based on the input, you could get one that is, horrible for your particular scenario. Okay, that's all for this video, and I'll see you in the next one.